Thank you and good morning. As you can see, the title of our talk is APT attack, threat-based purple teaming using attack. You might have noticed attack is in there twice. That's not an accident. We are big fans of attack. As introduction said, we are from MITRE. Before we continue, do a formal introduction. My name is Jamie Williams. I'm an adversarial engineer at MITRE. I do mostly research in adversary emulation as well as behavior detections. And some of the work you might have seen in the public space that I work on, MITRE attack, as well as attack evaluations. Am I not close enough to the mic? I'll get a little. Okay, that's a lot better. I can hear myself now. Okay.
And I'm Daniel Weiss. I'm a cybersecurity engineer at MITRE as well. I've been there for just about 3 years. I do both red and blue, split almost 50-50 right now, and I'm also on the attack evaluations team.
So as said, you might have noticed from the title of our deck, we are continuing a conversation or presentation from last year. So if you recognize those gentlemen, that's Cody and Chris, good friends of ours. They were here last year briefing on the same topic. So basically, and that shaped our talk today, is we're basically picking up where that conversation left off and giving a little more example and depth into threat-based purple teaming using attack. So before we continue, we'll do a quick recap of what they talked about last year. I think what is attack? That's a great start. The guys from Atomic Threat Coverage did a pretty good job yesterday describing attack, but at a high level, attack is our knowledge base of adversary behavior. Basically, the idea is we have this idea called threat-informed defense. Basically, if you understand what threats are doing, you are better equipped to make good decisions in terms of defense. One of my favorite things about attack is it's not theoretical. Everything that is an attack, all the behaviors captured there, are documented real behavior. So things adversaries are actually doing in the wild. We're not selling attack. It's free, global, open, so you can go to the website and read everything for free. There's no subscription. There's no money exchanged, as well as you can check out our analysis, as well as we reference everything. So you can check out the sources that we read to make these analysis and all these judgments. So we reference everything, you can click it and go to the ground truth intelligence there. And final point here is community driven. So if you've never noticed, a lot of attack comes from what we call contributions. So we have our contact information there. It's attack@mitre.org for email and our Twitter account. Definitely, we're always looking for, if you guys see things in the wild that are missing from attack, I think there was a mention of that yesterday, as well as there's a talk later today about cloud behaviors. Those type of things, we're always looking for new content, so definitely reach out. So to kind of give you an overview of the structure attack, normally you see attack in what we call the matrix view. So I've decomposed that to kind of make it make more sense. So starting with the tactics, or what we call the adversary goals. So these are, as you see across the top, we have the 12 what we call tactics. What's special here is this is not a kill chain, so there's no linear or set order of these. These are just basically the various different things an adversary would do in an environment once they're post-compromise. So things like gaining initial access, executing things, moving laterally, exfilling. And then on the end, we actually have, as of last week, our latest tactic, impacts. So attacks against availability and integrity. Coming down from every tactic, we have what we call techniques. So these are implementations of how an adversary actually achieves those goals. So for example, we look at cred access. You see things like brute forcing passwords, dumping passwords, or input capture, which is basically key logging. So capturing keystrokes to gain access to credentials. Within each technique, we have what we call procedures. So if you go to this page on the website and click on individual one, you'll see a full write-up on what we mean by that technique, as well as what we call procedures, which are actual malware or groups that have done this specific technique. So in this case, we're highlighting accessibility features. And as you see, that technique spans multiple tactics. So it's privesc and privilege persistence. So if you take a look at the procedures, it's kind of small, but basically you see how different groups have done accessibility features for persistence. So in the case of APT3, they replaced the setsc binary with their own payload. So when you go to an RDP desktop or a login page and hit shift 5 times, CMD will pop or the payload launches, as well as there's an Empire module that can do something similar. It replaces the magnify binary with CMD. So you go to a login page and you open the little magnifying glass, and instead of seeing a zoomed in thing, you see a CMD pop, and that's obviously malicious. So getting back to what Cody and Chris talked about last year, one of the things they were really excited about is what we call emulation plans. This is actually a new concept recently. Basically, the idea is taking these tactics from attack and mapping them into a structure for how you would emulate an adversary. So in this case, what they released the last CSharp was APT3. So they basically did a lot of research into the actual cadence of APT3, how they actually maneuver, starting with like the different phases. So getting their payloads ready and delivering it to a victim, what they do when they compromise a host. So like you see, evading defenses, discovery, privilege escalation. So there's various techniques within those tactics. And then phase 3, collecting exfil and like compressing and staging their data. A big point they talked about last year was using ATT&CK to evaluate specific techniques. So in this case, we have like what we call our Navigator. This basically allows you to make filters or highlight specific techniques and make your own matrix. So what they were talking about was basically, you select the techniques you're interested in, or even just one, and you use this purple teaming model to evaluate that. So basically the idea is you start with emulating a technique. So we figure out, in this case, execution through API. You figure out how an adversary would actually execute that, and you'd run it in your environment. And then on the blue perspective, you detect that or defend it however you choose. But the big point here is transparency between each end. So the red team is sharing with the blue exactly what happened, exactly when they did it, and completely telling you, there's no black box testing, so telling you exactly what happened and when, where, and how. Blue team defends it based on all that knowledge, pushes their defense back to red. So basically the challenge there is to up. So say, hey, now that I know you're defending it this way, can I do that same technique or behavior and bypass your new defense? So that iterative process going back and forth, as you can probably tell, like the level of like complexity and like resiliency increases each time. So you're probably thinking right now, like, am I going to spend the entire time talking about what happened last year? No. So thankfully, we do have some new content here, and it's actually pretty exciting for us. We're actually going to take a deeper dive into the science of what we're talking about by emulation and this purple teaming approach. So at a high level, just to kind of give you an overview of what we're going to talk about today, we're going to pick a specific technique based on a specific scenario, and then we're going to walk you through an example of the purple teaming approach. So emulating that behavior, defending against it, emulating again, defending against it, et cetera. But the big point here is transparency. So when we talk about purple teaming, the most important thing is that each side is talking to each other. So hopefully through our demonstration, we'll show you the importance of that and the value added by doing that. One assumption here is the technique that we're testing, we're starting from scratch. So we have no like something that we can apply as a defense. So we're starting from basically nothing for defending this technique. Okay, so we're researchers, so we kind of heads in the clouds very often. So one more thing we got to cover before we get like into the demonstrations. So it helps before you start thinking about emulation. It helps to think about like your emulation target. In this case, a behavior. When we talk about a behavior, we're not talking about things like static values like hashes, IPs, domains, strings, things like that. When we want to do what we call an emulation, we're emulating the action or the behavior, what an adversary actually does. If you're familiar with the pyramid of pain, this is like more the high-level things that are really hard to capture. So this is kind of like a nebulous concept. So a really interesting way to help you like understand what we mean by behavior is thinking about it in terms of attack. So like I said before, we have the tactics, techniques, and procedures. When we think behavior, we're more or less thinking the techniques and procedures. Excuse the pun, but like we think that's like more or less the heart of a behavior. It's the variation of the hows and the whats. And this is really important for emulation. Another way to think about a behavior is in stages. So if you think about like anything in the world, there's like before, during, and after. So in terms of a behavior, you can think about this, like apply that same model for behavior and think about the prerequisites. So what happens before a behavior happens, the mechanics, so what happens during the behavior, and then the artifacts, so what's left behind after behavior. So mapping that to sysmon events, we can think about like prerequisites, like things like image or driver loads, mechanics being things like process creates, process terminates, remote like memory reads, threads being created, things like that. So actually things happening, and then the artifacts being like more of the forensic side. So registry changes, file changes, as well as if you're talking about like beacons or rats, network connections that are left over that are like established C2 channels. So a lot of theory at this point, but at this point we try to get our hands dirty. We decided not to trust the demo gods, so we like pre-recorded all of our demos, but hopefully it's still kind of cool. So at this point, I'm going to hand over to Dan.
Sweet, thanks. So now that we know what a behavior is, we're going to actually jump into emulating one. Before we do, I'm just going to touch on how to do that. There's a bunch of open source frameworks out there to actually do that. The two I have up there are up there for a reason. One is because we open sourced it, and the other is because they kind of represent two sides of the emulation spectrum. You have the Atomic Red Team side, which is on purposely made to be simple and easy to execute. A lot of the stuff in Atomic Red Team are one-liners that you can copy and paste and run into your paste into your beacon or into a command prompt or PowerShell, for example, and just run, and then go through that purple teaming process. On the other side, you have a tool like Caldera, which is completely automated adversary emulation that does end-to-end attacks. And so, as part of our demo, we're kind of going to devise a scenario where we're going to demo indirect command execution. And indirect command execution basically says that we want to have a command line style interface without invoking CMD. At that same time, we also are going to avoid PowerShell. So as you can see in this example, running CMD is also blocked in this environment. So jumping to the Atomic Red Team, which is what we use for this demo for the easy side, if you go to indirect command execution on the Atomic Red Team, they actually have two different atomic tests that you can run. The first one is taking advantage of the program compatibility assistant, and the second one is for files. On the first one, the program compatibility assistant allows you to have that command line style interface. You just have to specify the -a flag. And for both demos, we are going to do the default value of just popping calc.exe. On the second one, the for files, there's three different command line arguments that we use. The first one is /p, which is the search path. The second one is /m, which is the search mask. So that basically says, it's a for loop and says, our search path is system32, and the mask, our search mask is notepad.exe. So for every notepad.exe that you see inside of system32, I want you to run the command after /c, which is calc.exe. And since there's only one notepad.exe in system32, it's going to pop one calc. And so just for the simple demo, on the left is the pca-lua.exe popping calc. I'm just doing it from the run window, so it pops through Explorer. And then on the second side, you can see for files also running through the run window, and that also pops calc. So sweet, simple demo. So now you see a pretty simple emulation of a technique or a behavior two different ways. And so now we'll jump into the blue side, or the detection side. And so before we jump into those two instances of detection, I just want to jump back and talk about how you actually come to a detection. So if you think of it from a pyramid-style layer, the bottom layer is going to be your data sources. That's going to be the source of your information, so process monitoring, image loads, DLLs, all those types of things. The second layer of that pyramid is going to be the sensors, so what actually is pulling or what's actually collecting the information from those data sources. And then the third is going to be your analysis on top of that, basically to formulate the detections. We have the Cyber Analytic Repository, car.mida.org. It's not listed up there, but that is one open source example of analysis on top of those sensors. And then just as a sidestep, I'll talk about Detection Lab real quick. We use that for all the demos. It's an awesome purple teaming environment. Red teamers can use it, blue teamers can use it. It's at a high level, it's just basically a Windows domain that you can stand up. Comes with a Splunk server, and you can customize it however you want. So usually how I run it is I throw sysmon on there. I open up sysmon to look like procmon. I enable a bunch of the advanced audit policies, so you get a whole bunch of Windows event logs besides the standard ones. And then you can run a emulation of a behavior like we just did in the previous slide, and you'll see literally everything that goes on underneath the hood of a Windows operating system. Okay, so jumping into that first test, which is the PCA-Lua exe. On the right, we have just a pretty simple process tree. So both of these tests are pretty straightforward. Explorer is going to pop the indirect command execution binary that we use, and that's actually going to pop calc. So going back to the data sources, if you want to detect the first test that we ran, the first data source, or the three data sources that you need for this behavior of T1202 is obviously process monitoring. You're going to want to monitor for process creations of the PCA-Lua binary. the command line parameter, so you have to specify that flag, the dash A, to run a process, to start a process, or to run your payload. And then like Windows event log 4688, obviously process creation will give you that. Also sysmon event ID 1, which is process creation for sysmon. And then jumping to 4 files, so same thing, pretty simple. 4 files pops calc. So you want to monitor for the 4 files binary or executable. And then from the command line parameter standpoint, 4 files, we use 3 in our test. So when you start doing this purple teaming and iterative cycle, you try to kind of break the detection. So in first, if we were looking for those 3 process command line parameter flags, the red team actually could devise a way that they can realize that they actually don't need those first 2 flags. So /p, the search path, you don't need. It defaults to the current directory, and you also don't need the /m, the search mask. It just defaults to a wildcard, so star. So if you're in a directory that has, for example, 3 files, it'll run your command 3 times. And you can also do it /c or -c, it doesn't matter. And then obviously the Windows event log data source, so 4688, that event, or if you're using sysmon event ID 1 will give you this information.
So we're going to take an opportunity to talk about the project we mentioned earlier, ATT&CK Evaluations. So if you've never seen this, this same kind of like red versus blue scenario, we basically, for ATT&CK Evaluations, we ran that same scenario against EDR products. So we have the URLs in the bottom, you can check it out, but basically we put together a 20-step red team script based on APT3, ran it, had EDR vendors set up the product, we ran that emulation against those products, and then provided the outputs of those EDR products, specifically focusing on detection. So if you see, as highlighted up there, you see on the left, you see the red side, so transparency, we're telling you exactly what we did. And on the right, we're showing you what the EDR product actually captured. So like, in terms of every technique that we tested, as well as what was captured there. So this is a pretty good like vignette for using this operationally or outside of just testing techniques. So going forward, like you said, Dan showed you, he said exactly what we tested, and he took that to the detection side, and using those command line arguments, was able to detect everything. I'm actually a huge fan of using like the red versus blue sparring analogy. I think it's great. Big point here, though, is it's really important sometimes to make blue miss. Not just like for shaming or anything like that, but actually like it's a good opportunity for leveling up. So showing them something that they've never seen to help them enable like growth and like learning. So big point here though is you're not just showing them things they've never seen, but scoping it to the realm of like real behaviors. So things they've seen that real adversaries are actually doing. So the next step in this emulation process is to emulate that same behavior, but better. The first step in that process is looking at the way the previous detection works. So like Dan just highlighted, everything basically on the PACLU and the 4 files detection was process-based. So looking at process creations as well as process command line arguments. So immediately as you start diving into the next level of emulation, your first prerequisite is, hey, I cannot live in that process land. So first thing comes to mind for me avoiding processes is .NET for many reasons. Firstly, it's pretty great in terms of like functionality, as access to the low-level like Win32 API, so you can do a lot of really creative things. In general, a lot of the detections for .NET is immature. Unfortunately, it's really complex under the hood, so there's really not a lot of great like automation and deep analysis and logic based on the mechanics that's going on in there. As well as, I mean, .NET isn't like inherently malicious. It's installed by default on, I think, everything past Vista. So there's a lot of noise and opportunities for false positives. So from an emulator or red team, it's a really great place to hide because there's a lot of normal activity happening in that realm. We call that like living off the land, so taking something that's already available and using it for malicious purposes. And finally, why this is a great emulation target is if you've followed a lot of like recent red team developments or frameworks, they're actually moving towards .NET, specifically C# to avoid like PowerShell, which also lives in that process level detection realm. And also like threat actors have moved here. So we've seen Chinese as well as Iranian actors leveraging .NET via C# for their malware kits. So starting to do research on how we're actually going to emulate this like indirect command execution that avoids CMD. We start taking a look and we come across this blog post about spoofing parent PIDs. So basically, C# .NET enables us to start calling API functions. One interesting function is create process. An interesting characteristic of create process, obviously it creates a process, but one of the parameters allows you to specify a particular parent PID. So that's super interesting. So we like, hey, that's something that we could potentially use to get past that CMD requirement. Taking a deeper look into this, we come across the proof of concept code. So if you've ever seen this, it's called select my parent. Basically, I think this was a Python script, but basically the idea is it implements that parent PID spoofing. So what it allows you to do is, if you look at the top, you give it a command, and then you give it a parent PID. And it basically launches that command as a sub process of that PID. So if you look at the bottom, it's actually like Procmon, or Process Explorer. You're able to see via this code, you were able to launch Notepad from LSASS, which is really weird and probably should never happen, but it's a really interesting characteristic of the way this API call works. So taking that to our emulation, what we're able to do is we found another POC for this written in C#, and we're able to launch that same calc payload, but from Explorer. So for the sake of demonstration, we left the command line arguments there so you can see them. But basically what's happening is we're launching calc from the parent PID of Explorer. And Dan will take a look at this on the detection side, but this is a really cool moment when you're doing this iterative emulation, because you finally found something that works, and you think it's really hard to detect, so you toss the ball back over to the blue side, and you're like, hey, good luck with that.
And so we'll accept the challenge of trying to detect this. What's really cool is C# and PowerShell both use the same underlying .NET framework, but C# doesn't have all the, from a defender side, C# doesn't have the same PowerShell logging. That is kind of why we want to avoid that as well. So basically what Jamie just explained is it's the same demo that we did before, but our C# payload is popping calc, but we're spoofing the parent PID, so it's actually spawning from Explorer. And going back to the data sources, the two that we used in the first two demos, process monitoring and process command line parameters, are not as useful in this case. One, you don't know what the process is going to be called, what it's going to be called when it's created. I guess you could search for if it's an unsigned process being started or an untrusted process being started, but that, from a malware standpoint, might not always be the case. And then as far as command line parameters, those are arbitrary. We could have obviously obfuscated those. We could have put them in base 64 and then decoded them on the fly. So from a command line parameter perspective, there's not much there. Fortunately, you can go buy some other data sources to kind of have some insight into .NET being executed. So actually first, I think I saw these on Twitter first. I'll have to throw the source in there after. But the two sysmon event IDs, 7 and 11. So image load, so the data sources tie back to loaded DLLs and DLL monitoring. There's actually two being loaded when you run a C# or .NET assembly. So it's the common language runtime DLL and the run just-in-time compiler DLL. So those two are loaded in when you run your .NET assembly, and then when you run your .NET assembly, a usage log file gets dropped into the user profile app data common language runtime usage log directory. So just interesting things that happen when you run .NET. So if that's not enough to convince you that .NET was running, you can also jump into ETW, which is event tracing for Windows, which is essentially a kernel level function or facility that enables you to log kernel and or application defined events to a log file. So there's 3 different providers that we'll kind of dive into for this purpose of detecting that demo. The first 2 obviously have to do with detection of .NET, and the third one, the kernel process, is going to be more as a bonus just to show that we can see the spoof parent PID. And then simply to capture or view these ETW events, there's a bunch of different ways. There's built-in command line, logman, and tracer PT, so you can run those built-in from the command line. And there's also some open source things. So FireEye released PyWinTrace, which is essentially a Python wrapper around ETW. And so for this demo, we actually are using another open source Python script called Dotnet Runtime ETW, which is made by Countercept, and it is a Python script that uses the Dotnet Runtime ETW provider, but it also leverages the PyWinTrace wrapper that FireEye made. And so when we ran that to capture those common language runtime events and all .NET events, this is kind of a blowout of what it looks like. So you do get a lot of data, but it is indicative of .NET running. So you can see the JIT events on the top. You can actually see like the f-kʒn demo, like the namespace and the class, and also the function, so main function and the create process function that were actually started. You can also see the module loads and stuff related to the .NET framework, as well as at the bottom you can see interop services as well. So all pretty indicative of .NET being run. And then as a bonus, I also said that I'd talk about how to spoof that parent PID, how to detect it. So that third ETW provider, which was the kernel process, there's another script. It's essentially just a wrapper. It'll run this ETW provider for you and then parse it out and show you the process spawned, the parent it spawned from, and then also the spoof parent. So if you use this ETW provider, the kernel process ETW, you can see effectively what happens. And it's in there for a reason. It's for UAC. So if you launch something from elevated prompt and you click yes through the consent.exe, this exists so the parent-child relationships match up, even though the elevated process is spawned from an SVC host. So this is actually, so there are false positives in here, but it's still cool that you can see the spoofed parent. And with that, you can give yourself a pat on the back.
That was really cool, but in reality, like scale that into an environment. Like take that and deploy it to 50,000 hosts, probably a nightmare. So the next step in this is like looking at that detection and actually detecting better behaviors better. So a big point here is the realization that maybe not every behavior is something that you should detect in real time for various reasons, such as like things like cost or noise. Like Dan was saying, false positives for that type of detection would be like horrific. You'd probably lose a lot of SOC analysts just quitting. The dashboard would light up immediately with all these like very benign things happening in the system, because everything we're dealing with here is built into the system and natural. They're also, so if you're not detecting things in real time, this may be an opportunity for you to leverage other business processes, so things like Hunt or IR. So if you're not going to detect it in real time, maybe that's something your Hunt team or your IR team will take responsibility for and say, they'll pick up where like the detections are missing. Another opportunity here would be something like protections. So an example of that would be if you looked at the most recent release of .NET, they implemented AMSI within the .NET runtime. So basically what that means is Windows Defender and AV products that are looking for signature-based malware and other heuristic behaviors are actually communicating with the .NET runtime and can give it like tips and hints on what's bad, what's good, and kind of like maybe prevent things that are super malicious or super obvious. So getting back to what we talked about before, that the stages of behavior and mapping this like better detection to this is actually will kind of help us scope like what's a realistic way to handle this. So mapping everything Dan just covered in the last section to these stages, so the prerequisites. The first thing you would see, like Dan said, those DLLs associated with .NET being loaded. So those would be prereqs. In the mechanics, you would see things like the process being created, as well as the events from the ETW, and then the artifacts being those log files written by the just-in-time compiler, as well as that log file in the user profile. So individually, all of these might be not great candidates for something to alert on, but if you map it out like this, you can kind of see potential, and I'm calling it a notional defensive approach, but a way you can actually build this into your defenses. So maybe a first step is, rather than firing on every time one of these individual things happen, maybe you set an alert for any time a process that is specifically unsigned is loading .NET DLLs. So maybe that might be outside of the scope of what real organic .NET execution looks like, because obviously everything in the system is probably Microsoft signed. A second step to that would be every time you fire an alert seeing an unsigned process loading .NET DLLs, you have an analyst follow up and take a look at those like very grainy log files, which would be a nightmare to parse and scale, but maybe an analyst has time to go look at those and actually do like an in-depth analysis. And for your hunters in the room, proactively look for this stuff. So inform your hunt team on all of this behavior, understand all these mechanics, And as they go around in the course of their normal behavior and look for things, they can take a look for these type of artifacts and do that kind of analysis before any of these behaviors actually happen. So kind of in conclusion, wrapping up what we talked about today, getting back to that attack matrix, basically what we did was, it's kind of nuanced and small, but that one technique that we're focused on, based on what we did, we're pretty sure we can take it from what we call low confidence to like medium. So we're not 100% sure we can detect that, but based on this iterative process, we feel like pretty comfortable that like we understand the behavior and how to detect it or defend against it, whether it's hunt, IR, or protections in our environment. So the next step would be rinse and repeat. So scale this same like process and activity out to all of the techniques that you care about. Another way of doing this is getting back to Cody and Chris from last year, chain them together into a full campaign. So rather than doing each individual one, you can actually write like an emulation plan that ties these together into like a cohesive like flow that goes over like, a couple days or a week, and then run all of this detection against the entire campaign based on those specific techniques. So this is our last slide. We'll leave this up. There's some good resources here. The top one is a link to attack. So everything else you could link from there, but specific things we want to call out is our Medium blog. So we have blog posts there for attack and attack evaluations, as well as like various use cases such as like blue teaming, hunting, SOC work, automation, et cetera. And the bottom two are our contact information. So our email and our Twitter. If you want to reach out about contributions or you have questions, or definitely tweet us with memes. We love memes. If you didn't notice by our slide deck, we're like eat, sleep, meme, just constantly trying to make each other laugh. So I think we have a couple minutes for questions. Otherwise, thank you for your time and your attention.
Thank you.